is about point geographic data, and I'll go through some various techniques that we use to symbolize and display point data within our maps. So point data, first of all, is the most common and the most simple form of geospatial data. We use that to represent discrete or independent data points. So these could be points of interest or particular features or field measurements, XY field measurements. And it can be scale dependent as well. So point data can become polygon data, as in the case of like a city into a city boundary polygon area, based on the scale in which you're displaying your map. And so, one of the simplest techniques that we have for visualizing point data is to simply put all the points on a map and then use a color-based symbology and levels of transparency in order to effectively symbolize that, so we're able to see patterns and clusters. The most common way to do this is what's known as the firefly cartographic technique, and that is where you have kind of a glowing effect. So that way you can place all your data on the map and you can symbolize all these various points, but there's not a data-based difference between those, but rather you're using various levels of transparency, so when there's clustering, they start to overlap and grow this kind of glowing field to them, that allows you to see where clusters of these events are happening. So in the case of an earthquake map like this, we can kind of clearly see just by placing a bunch of individual discrete points with this kind of glowing transparency on them, we can see pretty clearly the pattern that emerges. Similarly for hurricanes, and similarly for Sharknado threats. So this is what's known as the firefly technique. So what the firefly technique does is it uses a desaturated base map. It uses a single color point symbol, and that single color is highly saturated. So we use a very bright blue, a very bright green, a very bright red, for instance. So a highly saturated color of a single color for the point symbol, and then we have a gradient on that point symbol so that it goes from fully opaque in the middle, and then it has a gradient to transparent as we move away from the point. And we can set that gradient size however we want. It kind of depends on the scale of the map, how many points we have, etc. So this is kind of inspired by a lightsaber type of visualization, where we want something that glows in the middle and then kind of slowly fades as it gets away from the centroid point of that point data. So what the firefly technique is good for is it emphasizes the contrast between the data and the base layer. So you can really kind of see, this is especially true if you're using a very kind of broad geographic set of data like earthquakes or hurricanes or something that happens on a broad scale, and it allows you to see that contrast between the base map and the data very clearly. And it's good when you have lots of data. So if you have a bunch of data that exists, observations or events that happen with frequency over a broad geographic scale, it can be a very effective technique for kind of throwing all the data on the map, using this transparent gradient in order to kind of see what types of patterns emerge. And so this is effectively what the technique looks like, right? You'll have kind of these glowing spots, like start at a single color and kind of radiate out in a transparency. And it allows you to see different kinds of forms of patterns. When multiple transparencies overlap with each other, then it starts to create that compounding glow effect. So then you're able to see clusters of data, clusters of the event that you're looking for. So the firefly technique is very effective, and we'll practice this in our lab. It's very effective at highlighting the distribution of a bunch of data. Now, most of the time when we're looking at point data, what we're trying to do is symbolize that based on some sort of underlying quantitative variable. So in the case of this map, for instance, this is showing city population, and the size of that circle for the city is proportional to some sort of population or some sort of quantitative variable that underlies that. And so what this is doing is what's called thematic mapping or data-driven mapping. And what we're doing is we're associating a particular range or a particular set of visual variables. So the differentiation in how something changes based on its size, or its perspective height, or its lightness, or its hue, right? These different visual differentiations that we can have in our symbology, we're matching that to the data or the quantitative uh, differentiation of our geospatial data. So, for instance, when we're using point data, the most often visual variable that we'll use is size. And this essentially says that the size of the object that we're using, most often the case, point data, but it can be used with all sorts of vector data. But the size of the object itself um, is used to show proportional quantitative differences in the data. Right, so we can use this for point lines and polygons. It's most intuitive for point data, and line data to a lesser extent, and then with area data it can be a little bit more complex. And I have examples of all three to show you like how we can use that visual variable size to link the data with the symbology. And we can do this both in classified, which is known as graduated symbology, or unclassified, which is known as proportional symbology. So this is kind of the simplest form of that, right? Population by county or whatever kind of denomination this looks like county. And so then we have the size of the orange symbol is linked with the population of that county. And so here is an example of a proportional, right? There's a direct link between the data and the symbology size. And then this is an example of a classified where there is ranges of data, as you can see over here on the, as you can see over here in the legend, right, we have this range of 0 to 250,000, right? So all the counties that have a population between 0 and 250,000 are classified as the smallest symbol, and then so on and so forth. And I'll talk a little bit more about how we can derive, or what these different types of data classifications mean. So if we look at these two maps in comparison to each other, we can see that one represents population in one way, right? Showing kind of the range of the data in this case, right? Showing proportionally how much bigger LA County is than other counties, Cook County also being quite large, and then a lot of counties in New York metro area that make up the metropolitan population there. Whereas opposed to the graduated or the classified symbology, we have this allows us to see the distribution of the data a little bit more, right? We can see that there's a whole bunch of different counties that have this similar classification of less than 250,000 people, and then some counties or fewer counties that have kind of the various stages of the classes that we've decided. And like I said, we can use this for line data as well. This is common in what's known as flow maps. This is a map from Joseph Menard, who was a French cartographer the 19th century, who made a bunch of like hand-drawn maps of the flows of exports and imports from France. This is a map of wine exports from France, and it showed like where the wine that was being produced in France was going to in trade routes. And so these lines are proportional to the quantity of the wine that was being exported, and allows us to see kind of how that data distribution of movements are happening within this geographic space. It can also be effective for, so those are flow maps, and these are stream flow maps. It can also be an effective mechanism to show kind of volume of water, volume of river flows with the size of the river itself grows proportionally based on this amount of water in the watershed. So these are proportional flow maps or proportional stream flow maps. And then we can also use this size variable for what's known as cartograms. And cartograms is where the area of the geographic unit grows or shrinks based on different quantitative variables. So in this case, this is the amount of oil being produced. It's inflating the size of Middle Eastern countries and Nigeria and Venezuela, for example, inflating those size to uh, illustrate that they produce more oil in those places. So it gives us, a good sense of some proportional or some relative data comparisons between the places, but it can be a little funky to read, especially if you're not very familiar with, various geographic shapes and how things look. A cartogram, which is a proportional area map, can be difficult to read. Okay, so when we talk about our symbol size, we have to think about what is our minimum and our maximum size that we're creating in our map. So if we have the visual variable of size linked to some sort of quantitative difference in our data, then what's the minimum size, what's the minimum amount of data, and what's the minimum size of our symbology versus what's the maximum size of our data and the maximum size of our symbology. And in doing so, we have to take into account what's known as the Flannery composition, which is essentially a perceptual deterioration that happens, that when we're using, the more complex the symbology we're using, then the larger it gets, the more difficult time we have perceiving its relative size differentiation from smaller objects. So with lines, it can be quite easy to tell the size differentiation between those, because they're kind of simple linear features, and we're able to have pretty good fidelity between the actual length of that object and our perceived length of that object. Whereas when we get to area symbols, that fidelity erodes a little bit, and it's harder to tell. That's why pie charts are not very good geographic visualization or data visualizations, because it's hard to tell on circular objects that kind of area differentiation. And then when you get into three-dimensional objects, volumetric measurements, it becomes even more difficult to tell those kind of differences, especially the more subtle those differences are. It's hard to tell what that is, and our perception of the size differentiation loses its fidelity to the actual size differentiation. So oftentimes when we're making these proportional symbol maps and we're using point symbology, our absolute scaling might look something like this, and then our Flannery composition, which is a button that you can click within ArcGIS symbology tab, will basically just inflate the size comparison, just so it makes it a little bit easier to see the differentiation between the 300 and the 600, for instance. So that's a note, when you are making your maps and you see the little checkbox that says Flannery compensation, that's what it means. It's basically just saying, like, do you want to inflate the size of your symbology to make it easier to read? And oftentimes we just check yes, because it makes the map, it makes that like quantitative differentiation that we're trying to capture in the map easier for our audience to read. Some other considerations when we're making our point symbol maps is how are we breaking up the data. Whenever we do a data classification, we're making a decision about how much or where those breakpoints are in those classifications. And I'll talk more about that in a moment. But that distinction of like what type of data classification you're using, whether that's equal area, quantile, natural breaks, standard deviation, those are kind of the four main ones within your GIS software to use. That can make a big difference on what your map looks like. And so this map, for instance, this with the map that you'll be working on this upcoming week, mapping earthquakes in Alaska. This is using a certain data classification here that represents the distribution of the earthquake data in a particular way. And this is another data classification that's representing it. So it's all the same data, but it's representing it in slightly different ways because it's using a different data classification method, whereas this one is representing it, again, slightly different. So if we look at these three, all three of them are the same data, the same number of classes, but then distinguishing between natural breaks, equal interval, and quantile yields different looking results of what that kind of distribution of earthquakes within this region is, right? And so I don't want to spoil, this is part of one of the questions on the quiz, so I don't want to give the answer away right now, but keep in mind of like what each of these are doing when you're kind of exploring the different data classification methodologies. what each one's doing and how that's kind of changing how your map looks. We also have to make the decision when we're making maps with these size variables is how many different classes we're going to have. And so the number of classes, how many different bins or how many different uh, breaks are there within our range of data. And so oftentimes, if you think about how many different bins are there in this map or how many different classes there are, there's 4, right? Oftentimes when using a uh, size as a visual variable, 4 is a good number. Seeing 4 different data classes is pretty easy, and we can kind of keep what's known as a high level of legend to map fidelity, right? That we can look at the legend, get a sense of what the different data classes are, look at the map, and if we have 4 classes, we're able to kind of like remember what those differentiations are. We don't have to keep referring back and forth between the legend and the map, right? And so the less time that your audience has to spend, less labor that your audience has to spend looking back and forth between your map display and your legend display, right? The easier that is for your reader to kind of comprehend what you're trying to get across in your map. Whereas if you have 6 classifications like this, not only does that make the distinction between those classes, you have to be more thoughtful about exactly how you're visualizing those so that you can see more easily what those differences are. But then in this case as well, there's not very good fidelity between the map symbology and the legend symbology. So every time you look at the map, let's say you look at Wyoming, you kind of have to refer back to the legend to see where that is. You go to the next state, you kind of have to refer back to the legend to see where that falls. And so in this case, that's kind of like a bad symbolization because there's too many classes, and that differentiation between the classes is not enough to really keep that mental memory of what the classes are between each portion of the map page or the map layout you're looking at. And then we talk about symbol color as well. Typically when we're doing a size-based visual variation with our point data, we want to keep that single color. And so if we think about the differences in sizes as being the differentiation between one set of quantitative variables, right? Say that's population, for instance, of cities, then we'll keep the size will be the visual representation of that quantitative variable. And if we add an additional visual variable, often people will want to use color as well as size within their map symbology. If you do that, then that's often leads to confusion because you have too many things. You have 2 different types of visual variables operating with one type of data, right? And so if you're trying to do a multivariant visualization, then you want to make sure you're representing different dimensions of the data at the same time. So if looking back at this Alaska map, right, if these colors were, or if this yellow was also visualized with a color gradient, then you're just kind of adding confusion or adding unnecessary information to your map, where what you're trying to do is keep it kind of as clean and as simple as possible so that the reader can look at this and just kind of easily tell that there is a magnitudinal differences in these earthquakes, and that's represented very clearly by the size of the point symbol. Sometimes if you're using multivariant data, then you might use multi-symbology, right? So in this case, you're mapping both. This is for a Zika travel advisory. So in this case, you're mapping both the number of monthly arrivals from countries with the CDC Zika travel advisory, and you're mapping the potential abundance of this pathogen, right? So you're mapping simultaneously both the climatic variables that allow for this particular pathogen to proliferate and the amount of people coming into that space. So in this case, you have 2 different variables that you're mapping, and so then that you can use 2 different visual variables or 2 different symbology variables to capture that. And so you have size here representing basically international inbound airport flights, right? And then you have the red indicating kind of these climactic variables. And so then from that, we're able to see, even though there's a high amount of people coming into LA and Dallas, for instance, those are not as high of concern as maybe places like Orlando, um, or even Charleston, that have fewer people coming in, but then have a higher potential uh, for this outbreak to happen. So this is the case of using multivariable symbology. Here's another multivariable symbology. You can see, you know, once you get into these multiple variable symbologies, this is looking at rental prices and amount of Section 8 vouchers in particular areas in Portland. You can see that once you kind of start getting into these multi-symbology displays, though they can be really effective and really uh, strong at pulling out like corollaries between the two different variables you're mapping, it also like creates a more difficult legend and a more kind of, you have to be much more specific in like how you're classifying your data and how you're relating the information, so that you have uh, a complex, so your complex legend is matching the data and showing that kind of relational values between the two. So it can be hard to kind of scale those, because often those are using two different scalar units on the y-axis and the x-axis. As you can see here, one's in income and the other one's in kind of a nominal value of vouchers, right? And so then that way you have kind of a, not disconnect, but it just requires a little bit more attention to detail to make sure you have this type of legend is classified so it can symbolize on the map appropriately. So long story short, when most situations call for a single color variable of your maps to keep things as simple as possible. You also have the option within ArcPro to include pie charts as your visual variable, so you can make sized pie charts that will then represent multiple datas within kind of a point symbology. And I always highly encourage you not to do this for any reason whatsoever. Anytime you can avoid using pie charts for any reason for the rest of your life, I would definitely encourage you to avoid using pie charts. Just because they're not only are they, you have that kind of Flannery composition where it's hard to see that size differential between this one here and this one here, for instance. And it's hard to get that kind of proportional difference between those. But then also once you start breaking those up into pieces and segments, it becomes increasingly difficult to kind of make sense of them. So typically I say, do whatever you can do to avoid using a pie chart, basically. All right. And then symbol shapes, typically we use circles. They're the more intuitive, the more kind of easy to read of the different types of point symbols that we can use. And so usually a circle shape is the best shape, but you can use other shapes as well. And for sometimes, a pictorial symbol like an airplane or a liter of beer or other non-circle geometric symbols could be appropriate depending on your map application. Oftentimes, I say 95% of the time the circle's the best choice, but there are occasions when, something else, whether that's like a very specific thematic type of map you're making for air travel or for drinking behaviors, for instance, or if the shape of your geographic areas lends itself to a more square symbology, sometimes that can be effective as well. But oftentimes, circle is the way to go, more often than not. Here's some examples of the square, and you can see that because it's square, it can kind of make it hard, especially in overlapping data like this, to kind of make sense of the boundaries a bit more. Whereas if you have circle data, you can it kind of deals better with the overlapping data more than square does. So that's why we typically use circle, because oftentimes when we're using point symbols, they often overlap. They're often clustered because they are typically representative of population or some sort of variable that often, some sort of human related variable that often clusters. And so depicting clustering with these square symbologies or these pictorial symbologies can be quite difficult. If they're a little bit more spread out, it can be a little bit easier. But especially if things are overlapping like this, then circles 99% of the time the best way to go. And you can see here, having some sort of raindrop type of thing for water it can just make it a little bit convoluted looking. And then kind of the final point on these point symbol maps is that this graduated point symbology is best suited for real point data, not for the centroids of polygons, right? If you don't want to take state data and reduce that state data down to a centroid point, which you can easily do, but you don't want to do that and then represent that with this sized base symbology. Typically if we have, typically we want to symbolize the data within the geographic topology that it exists within. So if it exists within uh, polygon data, if it's county data or state data or some sort of other kind of geographic census-based unit, we want to keep it in that. So because when we transform it from point to polygon or from polygon to point, or when we already have those kind of like topological transformations, we lose certain aspects to the data in that capacity. So for example, this is a set of point data that uses a size-based symbology for different cities in Indonesia. And this works well. Even in these overlapped areas, you can kind of see this stacking and clustering. You can see that it works pretty effectively at illustrating where the high population and the sparsely populated places are within this, very large country. Again, kind of the same thing here. You can see pretty effectively that these circles can capture population. They can capture the overlap pretty effectively and show you a good sense of the distribution of population in the country. Whereas if you use these point symbols as centroids to the state, like in this case, it tells us something, but it's just not the most optimal or the most effective way to symbolize this data, right? This data is not point data, but this data is aggregated data within South Dakota, right? This is a count of particular points within an aggregated unit, and then it's transformed back to a point for symbolization, and that's just like not the best pathway for symbolizing this type of data. If you're doing that, you want to use what's called a choropleth map, or a color-based symbology of area units, which we'll talk about in a couple weeks. All right, and then finally, so that's the two types of point symbol symbolization that we've talked about thus far. The firefly technique, which is good for symbolizing a bunch of data and not necessarily making a data-based classification from that, but just showing a bunch of different point data so that the user can get a general sense of the overlying or the underlying distribution, spatial distribution of the data. And then we also have our graduated point symbology technique, which allows us to use the visual variable size to depict the quantitative differences of particular point locations. Right, so that's a data-driven technique. The first one's a visualization-driven technique. And then we have our third one, which is called heat maps, which is really kind of a interpolation or a density measurement technique. Yeah, so the heat map, basically what we're doing is we're collecting or depicting all of the point data in our map, and we're kind of transforming that point data into a surface, right? A surface of events that are happening. So it's taking a range, it's taking kind of a spectral range of data that goes from cool, that represents low density, to warm, that represents high density. So it can kind of mimic like a thermo image that you would see for something like this, right? So this is like what the heat map technique is for like depicting in like thermal imagery, for depicting life, forms, body heat, etc. So we're using that same technique and saying the areas that have high density, we're going to represent them as warm, and the areas that have low density, we're going to represent those as cool. And so basically how we do this, say we have a bunch of point data scattered throughout a landscape. Let's say we're looking at this one. This is point data for people that use their phones to call an Uber at 2 a.m. on a Saturday in New York, right? So we can tell from this, that there's a distribution of where people are using their phones at, kind of within these areas where there's likely events ending, concerts ending, bars closing. Though bars don't really close in New York, but you know what I mean, like the various times when certain bars close or certain things happen and whatnot. And so you can see from this that there's like a lot of people that are using their phones here, a lot of people are using their phones here, a lot of people are using their phones here, and then there's a decay away as you get away from these points. And so that allows us to use a heat map, get a relative uh, surface density of where these different point events are happening, and then from that we can create an interpolated surface of, or a raster surface of kind of population use at this time, right? So we say, oh, if a bunch of people are using their phones here, then there's kind of like a decay between these points, right? There's known data here, known data here, and we're going to like infer what's going on in between those known data points. So with that, we use what's known as a kernel density function. That's how we make a heat map. We have a moving window that calculates the local density, and we can dictate what the size and the shape of that kernel is. And so how it calculates density based on the surface, like we can use a variety of different understandings of the natural landscape or the phenomena that we're using, or different scalar units to determine what's the size and what's the shape of that kernel as it moves across the landscape to calculate, how many instances are happening within each segment of that moving window. So for instance, if our image is doing this, right, our kernel density is doing this, it's going through and it's calculating, the sum of what's happening or the count of what's happening within each of these points in the raster, and then creating a new surface based on that function. So in ArcGIS Pro, in old versions of Arc, you would have to kind of do this manually. In ArcGIS Pro, there's a symbolization feature on your point data that says heat map that basically does this for you, so you don't have to actually go through the process of doing the raster calculator function like you used to. There's a kind of a simple symbology way to do it, but that's kind of what that heat map function is doing behind the scenes, is using a moving window to cycle through your data, and whatever the kind of mathematical operation you're asking it to do, is performing that and then rewriting it to a new raster in this way. So we have heat maps that we create from a set of points, and this is really good for representing our point data as a continuous surface, right? So if we want to know, we know a bunch of observed locations, say that's of tree measurements in the field, or of fire disturbances, or of instances of crime or whatever in the city. We have all these point data where there's known information, and then we want to infer what the broader landscape is based on these known observations. So we want to take discrete point data and transform it to a continuous data representation. A heat map is very well suited for that particular representation. So there's also the assumption when you do that is that your known data is not capturing all the events that are happening, right? That your known data is capturing a subset of the events or a sample of the events, and then with that interpolation method, then you can infer what you don't measure directly, right? And so in the map that you're doing this week, that's using the heat map technique as part of the quiz, you're doing a map on rat sightings in New York City, under the assumption that not all rats are seen. So if we take the known observations of rat sightings, then we can infer a broader landscape of rat territory within the city. Yeah, so heat maps are very often used for urban planning, transportation analysis, epidemiology. In forestry, it's used for tree disturbances, or things like that. That you take a sample of a data, and then you can infer the broader pattern based on that sampling when you transform that data from discrete points into a continuous surface. So here's an example of what heat maps might look like for transportation analysis, etc. So yeah, that's a heat map. So those are the three techniques that we often use with point data. We use the firefly technique, so we can see the broader pattern. We use the graduated point symbology, so we can see the quantitative differences in the data. And we use the heat map technique, so we can see, or so we can infer a broader pattern based on known points. All right, so that is all for point symbology. Your map this week you have the quiz where you run through 3 different processes where you use all 3 of these to make the to make 3 different samplings, and then you create one map of the earthquakes in Alaska. So let me know if you have any questions. I will see you in lab this week.